In the previous lecture, we started the topic of 2 degree of freedom systems, in which we discussed the theoretical details of a 2 degree of freedom system. We discussed what is a 2 degree of freedom system, how it differs from the single degree of freedom system, what are its equations of motions, what are the real world examples of 2 degree of freedom systems, what is the concept of finding out degrees of freedom in the light of number of masses and number of possible motions, what is the concept of coordinate coupling, and how to determine the natural frequencies and mode shapes or natural mode shapes for such a system. So in this lecture we will start solving some numerical problems in order to develop better understanding of 2 degree of freedom systems. So let's get started. So first of all, we have a very basic numerical problem in which the concept of equations of motion for 2 degrees of freedom system and the concept of coupling is discussed. The problem states that using x and theta coordinates, derive the differential equations of the system as shown in figure. Also identify the coupling. So as it is shown in figure, that the system consists of a rigid bar which is supported on two stiffness elements, each having stiffness equal to K. On the left hand side, the stiffness element is located or placed at a distance L by 4 from the center of gravity of the bar. Similarly, on the right hand side, the stiffness element is placed on the extreme right end or at a distance of L by 2 from the center of the bar or CG of the bar. So when the system is excited under the action of the externally applied force, the system will undergo two different types of motions. Number one, the bar will compress up and down, or the bar will move up and down in the vertical direction. That means the bar will undergo the linear motion or translatory motion, that is x of t. Also, due to the moments produced by the stiffness elements, the bar will also tend to rotate about its center of gravity, or in other words, a moment is produced in the bar about its CG, thus producing a moment equal to m as a function of t. So before moving on deriving the equations of motion for this given system, first we have to draw its free body diagram as it is shown in figure. So after drawing the free body diagram in which the both possible modes of motions are shown, then we proceed to the next step in which we write down the equations of motion for each type of motion, that is translatory motion and rotational motion, using the Newton's second law of motion as follows. First we consider the translatory motion of the bar, that is summation f is equal to mx double dot, and by using the free body diagram it is clear that the summation of f is equal to minus k into x minus L by 4 theta minus k into x plus L by 2 theta, which is equal to mx double dot. In this equation it should be noted that we take out k as a common factor, where kx is the spring force produced by the stiffness elements k, and k into L by 4 theta comes from the relation S is equal to R theta, due to the fact that when the rigid bar tends to rotate about its CG, it will produce an arc length which is equal to S is equal to R theta, And for this system, the arc length is given by L by 4 theta. So multiply this arc length by the stiffness element, we get the force of our given system according to the corresponding stiffness elements. So after applying simplification procedure, the above equation becomes mx double dot plus 2kx plus 1 by 4 kl theta is equal to 0, and we may call this equation as equation 1. So this is the equation of motion which is related to the first type of motion, which is the translatory motion. Next, we will consider the rotation of the bar about its CG, or the equation of motion, which consists of the moment produced by the stiffness elements of the bar around its center of gravity. So it becomes summation m is equal to j theta double dot. As you might remember that in the video lectures of chapter 2, we discussed that how the Newton's second of motion for the moments form can be written as m is equal to j theta double dot. It should also be noted that here we are taking the clockwise moments as positive. So the equation becomes m of t plus k into x minus L by 4 theta into L by 4 minus k into x plus L by 2 theta into L by 2, which is equal to j theta double dot, where j is the polar moment of inertia and theta double dot is the angular velocity. Like the previous equation, in this equation we also take out stiffness element k as a common factor, and here kx is the force produced by the stiffness element in the vertical direction, and k into L by 4 theta is the force of the stiffness element when it tends to turn the rigid bar about its center of gravity, thus producing an arc length which is equal to S is equal to r theta. So after multiplying these forces with their corresponding moment arms, that is L by 4 and L by 2 respectively, we get the moments for this system. So after simplification process, the above equation reduces to the form j theta double dot plus kl upon 4 into x plus 5kl square upon 16 into theta is equal to m of t, and we may call this equation as equation 2. So these are the two equations of motion for the given system, and these equations of motions may be expressed or written in the matrix form as follows: matrix M00J into matrix x double dot theta double dot plus matrix 2k 1 by 4 kl 1 by 4 kl 5kl square upon 16 multiplied by matrix x theta is equal to matrix 0 m of t. So as you can see, in this matrix form we have two matrices involved. First is the mass matrix and other is the stiffness matrix. Since it can be seen from this form that the mass matrix is diagonal in nature, because the diagonal terms contains the mass and the polar moment of inertia, while the other terms are zero. And as we studied earlier in the previous lecture, that in order to comply for the inertial coupling, the mass matrix must be non-diagonal. So for the system, the inertial coupling is absent. However, if we closely look at the stiffness matrix, then we come to know that the stiffness matrix is non-diagonal, and since it is non-diagonal in nature. Therefore, the system has elastic or static coupling. So that's the end of the first numerical problem. Next, we have another numerical problem, which is problem 5.4 from the book S.S. Rao 5th edition, and it states that a two-mass system consists of a piston of mass m1 connected by two elastic springs that moves inside a tube as shown in figure. A pendulum of length L and mass m2 is also connected to the piston. Derive the equations of motion of the system in terms of x1t and x2t. So by closely looking at the given figure, it comes to know that in this system we have two masses. First, the mass m1, which is attached between two stiffness elements having stiffnesses k1 and k2. These stiffness elements are fixed to the two different fixed supports. Also, the mass m1 translates linearly in the direction having displacement x1 as a function of time. Then a pendulum having end mass m2 is attached to the center of mass m1. So when the pendulum oscillates with angular displacement theta, the mass m1 translates in the direction of x1t, which means the pendulum also translates having some linear displacement, let's say called it the displacement x2 of t, when the mass translates. So the angular motion of the pendulum induces a linear motion in the mass m1, and since the pendulum is attached to the center of mass m1, the pendulum also oscillates in the linear direction, or in other words, the pendulum also performs linear motion or translatory motion. So before formulating the equations of motion for the given system, we have to draw the free body diagram for the individual masses which are involved in the system. So first take the pendulum end mass, which is m2, and draw its free body diagram. By assuming the string of the pendulum having negligible mass, we only consider the end mass of the pendulum as m2, and after drawing its free body diagram, it comes to know that there are two forces acting on this end mass m2. First is the weight of the mass m2, which is acting in the downward direction, and it is equal to m2g. The other is the tension in the string or thread, which balances the mass m2. Since the pendulum is oscillating with angular displacement theta, therefore the tension force T has some angular components. So after resolving the components in the vertical direction, it comes to know that the component of tension which is in the direction of the weight force is T cos theta, or after applying equations of equilibrium or conditions of equilibrium in the vertical direction, it comes to know summation F is equal to 0, and it should be noted that here we are taking all the vertical forces in the upward direction as positive. So T cos theta minus W is equal to 0, and by substituting the value of W in the above equation, we get T cos theta is equal to m2g, or T is equal to m2g upon cos theta. Since the pendulum is oscillating with some angular displacement theta, and the pendulum is also attached to mass m1, which is also oscillating in the linear direction. Therefore, the pendulum will oscillate with minimum angular deflection, that is minimum theta, and for small values of theta, cos theta is approximately equal to 1. Therefore, the above equation reduces to T is equal to m2g. So this is the equation of motion for the second mass, and in this equation only vertical forces acting on the pendulum are considered. So in the next equation we will consider the horizontal forces acting on the pendulum. For this purpose, the modified free body diagram will be used to study the motion of pendulum, in which we will also consider the motion of mass m1, which is translating linearly between the stiffness elements k1 and k2. Therefore, we have summation f is equal to mx2 double dot, and here we are taking all the linear forces which are horizontal, and all the forces which are acting from left to right are taken as positive. Therefore, minus t sine theta is equal to m2x2 double dot, or by substituting the value of t, which is calculated in the previous equation, we have t is equal to m2g, and the above equation becomes m2x2 double dot plus m2g into x2 minus x1 upon L is equal to 0, where the value x2 minus x1 upon L is the value of trigonometric function sine theta, which has been found out from the free body diagram, in the sense that perpendicular is equal to the distance x2 minus x1, and the hypotenuse in this equation is the string length L. So the above equation reduces to m2x2 double dot minus m2g upon L into x1 plus m2g upon L into x2 is equal to 0. So in the next step, we will consider the motion of mass m1 by drawing its free body diagram as shown in figure. Therefore, by applying the conditions of equilibrium in the horizontal direction, we get summation f is equal to m1 x1 double dot, and here we are taking all the horizontal forces which are from left to right as positive. Hence, t sine theta minus k1 x1 minus k2 x1 is equal to m1 x1 double dot. Since from the free body diagram it is given that sine theta is equal to x2 minus x1 upon L, due to the fact that sine theta is a trigonometric function and it is equal to perpendicular upon hypotenuse. So in the next step, by substituting the value of sine theta, we get m1 x1 double dot plus k1 x1 plus k2 x1 minus t into x2 minus x1 upon L is equal to 0, or m1 x1 double dot plus k1 plus k2 plus m2g upon L into x1 minus m2g upon L into x2 is equal to 0. So in this case, the equations of motion for this 2 degree of freedom system are derived in terms of the linear displacements, that is x1 and x2 as a function of time. So with this, the problem 5.4 ends here. The next problem is the extension of problem 5.4, in which the values of the masses m1 and m2 and the stiffness elements k1 and k2 and the length of the string are given, and we are required to find the natural frequencies of the system and the amplitude ratios. So the problem states that if m1 is equal to 5 kg, m2 is equal to 1 kg, k1 is equal to 0.8 kilonewton per meter, k2 is equal to 0.2 kilonewton per meter, and L is equal to 1 meter, find equations of motion in x1 and theta coordinates, natural frequencies, and amplitude ratios. So the solution of this problem begins with the end of the previous problem, in which we have already derived the equations of motion for both the masses m1 and m2 respectively. So after substituting the value of mass m2 in the equation of equilibrium of the pendulum in the vertical direction, we get T is equal to m2g, or T is equal to 9.8 newtons. Similarly, recall the equation of equilibrium for mass m1 in the horizontal direction, which was T sine theta minus k1 x1 minus k2 x1 is equal to m1 x1 double dot. Since the pendulum is attached with mass m1 and with the linear oscillation of mass m1, the pendulum also oscillates and performs two types of motions. First is the translatory motion in the x direction, and other is the rotational motion about its pivot point at mass m1. So with the oscillation of mass m1 in the x direction, the end mass m2 of the pendulum will also oscillate with minimum angular deflection, that is theta, and for small values of theta, the trigonometric function sine theta becomes theta. Therefore, the above equation becomes m1 x1 double dot plus k1 plus k2 into x1 minus t theta is equal to 0, or by substituting the values of m1, k1 and k2 and t in the above equation, we get 5x1 double dot plus 0.8 plus 0.2 into x1 minus 9.8 theta is equal to 0. Since we are required to find out the equations of motion for the system in terms of x1 and theta coordinates, therefore for end mass m2 of the pendulum, we will draw another free body diagram which shows the moment produced by the end mass of pendulum about its pivot point, which is at the center of mass m1, and we take the pivot point as O, and after applying the Newton's second law of motion, we get summation m is equal to j theta double dot, and here we are taking all the anti-clockwise moments as positive. Therefore, we have minus m2g sine theta L is equal to j theta double dot. Since, as described earlier, that for very small angular displacements theta, the trigonometric function sine theta becomes theta. Therefore, we have j theta double dot plus m2gl theta is equal to 0, or m2l squared theta double dot plus m2gl theta is equal to 0. In this step, the value m2l squared is the polar moment of inertia of the string about the pivot point O, and by substituting the value of m2 and L in the above equation, we get theta double dot plus 9.8 into theta is equal to 0. So these are the equations of motion for the given system in terms of x1 and theta coordinates. So the solution of the above highlighted equation can also be expressed in the harmonic form as theta of t is equal to x2 into cos omega 1t, where theta, that is the angular displacement, is a function of time, x2 is the amplitude of vibration of the second mass, that is point mass of the pendulum, and omega 1 is the natural frequency for the system, which is equal to under root 9.8, and omega 1 is equal to 3.13 radian per second. So by substituting the value theta of t is equal to x2 cos omega 1t in the equation of equilibrium of mass m1, which is highlighted, we get 5x1 double dot plus 1000 x1 minus 9.8 x2 cos omega 1t is equal to 0, or 5x1 double dot plus 1000 x1 is equal to 9.8 x2 cos omega 1t, or 5x1 double dot plus 1000 x1 is equal to f cos omega 1t. So we may call this equation as equation A, and it is the undamped forced vibration. It should also be noted that the force is provided by the tension in the cord. So the equation A becomes omega 2 is equal to under root k upon m is equal to under root 1000 upon 5, and omega 2 is equal to 14.12 radian per second. So we have the natural frequencies are omega 1 is equal to 3.13 radian per second, and omega 2 is equal to 14.12 radian per second. The response of the system is given by the equation A as follows: x1 is equal to f upon k minus m omega square, or x1 is equal to 9.8 x2 divided by 1000 minus 5 omega square, or x2 upon x1 is equal to 1000 minus 5 omega square upon 9.8, where the expression x2 upon x1 represents the mode shape of the system. And with this mode shape, this numerical problem ends here with following conclusions. Number 1, if the system is made to vibrate at the pendulum's natural frequency, the amplitude x2 will be large. Number 2, if the system is to vibrate at the frequency of mass m1, x2 will be very small as compared to x1. And number 3, from the equations of motion, it is observed that the motion of x1 has no effect on motion theta. However, the motion of theta affects the motion x1, hence theta is the controlling variable in this problem. Therefore, x2 can be the initial condition for the system, and the motion of the pendulum will reduce the force vibrations in the mass m1. So next we have another problem which states that for the figure and the data given, find the natural frequencies, the mode shapes, and the response of the system. So as the figure shows, the system is composed of two masses m1 and m2, which are connected by the stiffness elements k1 and k2 in such a way that the stiffness element k1 is connected to the fixed support. The other end of the stiffness element k1 is connected to mass m1, while the other end of the mass m1 is connected to the stiffness element k2, and the stiffness element k2 is connected to the mass m2 at its other end. The masses m1 and m2 are translating with the displacements x1 and x2 respectively. We are given with the values of m1 and m2 as m1 is equal to 10 kg and m2 is equal to 1 kg. Also, the stiffnesses K1 and K2 are given as 30 Newton per meter and 5 Newton per meter respectively. Also, the initial conditions for the system are given as x1 of 0 is equal to 1. Therefore, derivative of x1 at 0 is equal to 0. Also, x2 of 0 is equal to 0 and its derivative at 0 is also 0. So, the solution starts with the formulation of equations of motion in such a way that each mass, that is m1 and m2, is evaluated separately. First, we will draw the free body diagram of the mass m1 and then formulate its equation of motion. The free body diagram of m1 as shown in figure, and it shows that m1 is compressing k1 while at the same time m1 is stretching k2. So m1 is moving between the two nodes x1 and x2. So by applying the Newton's second law of motion on m1, we get summation f is equal to m1 x1 double dot, and here we are taking all the horizontal forces which are from left to right as positive. Therefore, we have minus k1 x1 minus k2 into x1 minus x2 is equal to m1 x1 double dot, or m1 x1 double dot plus k1 x1 plus k2 into x1 minus x2 is equal to 0. By substituting the values of m1, k1 and k2 in the above equation, we get 10 x1 double dot plus 35 x1 minus 5 x2 is equal to 0, and we may call this equation as equation 1. Next, we will draw the free body diagram of m2, and it shows that the mass m2 is moved by the spring action of the stiffness element k2, and it is moving between the nodes x1 and x2. Therefore, by applying the equations of equilibrium on the mass m2, we have summation f is equal to m2 x2 double dot, or k2 into x1 minus x2 is equal to m2 x2 double dot, or m2 x2 double dot minus k2 x1 plus k2 x2 is equal to 0. Therefore, by substituting the values of m2, k1 and k2 in the above equation, we get x2 double dot minus 5x1 plus 5x2 is equal to 0, and we may call this equation as equation 2. So equations 1 and equation 2 are the equations of motion for this 2 degree of freedom system. Next, in order to find out the natural frequencies for the given system, first we have to suppose a harmonic solution for the system, and for the system to be in harmonic motion, we have x1 is equal to capital X1 cos of omega t plus phi, and x2 is equal to capital X2 into cos of omega t plus phi, where x1 and x2 are the displacements of the masses m1 and m2 respectively, and capital X1 and capital X2 are the amplitudes of the two masses, and omega is the natural frequency and phi is the phase angle. If we closely look at these harmonic equations, then it is evident that the amplitude of both the masses can take different values, but their frequency and phase angles will be same. So, taking the double derivative of these harmonic equations x1 and x2, we get x1 double dot is equal to minus x1 omega square cos of omega t plus phi, and x2 double dot is equal to minus x2 omega square cos of omega t plus phi. So by substituting these values of x1 double dot and x2 double dot in the equations of motion of the two masses, that is equations 1 and 2, we get equation 1 implies that minus 10x1 omega square cos of omega t plus phi plus 35x1 cos of omega t plus phi minus x2 cos of omega t plus phi is equal to 0. Since the trigonometric function cos of omega t plus phi cannot be equal to 0, therefore we have minus 10 omega square plus 35 into x1 minus 5 x2 is equal to 0, and we may call this equation as equation 3. Next, the equation 2 becomes minus x2 omega square cos of omega t plus phi minus 5x1 cos of omega t plus phi plus 5x2 cos of omega t plus phi is equal to 0, or minus omega square plus 5 into x2 minus 5x1 is equal to 0, or minus 5x1 plus minus omega square plus 5 into x2 is equal to 0, and this equation is called as equation 4. Equations 3 and 4 can be written down in the matrix form as follows. Matrix minus 10 omega square plus 35 minus 5 minus 5 minus omega square plus 5 multiplied by matrix x1 x2 is equal to 0. Since the solution of these equations is possible if the determinant of the coefficient matrix, which is highlighted in the red box, is equal to 0. Therefore, we have determinant minus 10 omega square plus 35 minus 5 minus 5 minus omega square plus 5 is equal to 0. And after opening the determinant, we get the following equation having polynomial degree of 4. That is 10 omega raised to the power 4 minus 85 omega square plus 150 is equal to 0. Since for simplicity we are assuming omega square as some variable, let's say z is equal to omega square. So after substituting this value in the above equation, we get 10z square minus 85z plus 150 is equal to 0. So as you can see, after substituting the value of omega square as a variable z, the above equation is reduced in the form of quadratic equation whose solution is relatively simple. So after solving this quadratic equation, the roots of the equations are z1 is equal to 6 and z2 is equal to 2.5. Since z is equal to omega square, therefore omega 1 is equal to under root z1, which is equal to under root 6, and omega 1 is equal to 2.45 radian per second. Similarly, omega 2 is equal to under root 2.5 and omega 2 is equal to 1.58 radian per second. Next, we will find out the mode shapes, which are basically the displacement or deformation patterns which a vibrating body or structure will acquire when it is made to vibrate at a given frequency. So the mode shapes of the system are found out by simply substituting the values of omega 1 and omega 2 in equations 3 or 4. Therefore, by substituting omega 1 is equal to 2.5 radian per second in equation 4, we get minus 5x1 is equal to minus into minus omega square plus 5x2, or x12 upon x11 is equal to R1, which is equal to 5 upon minus omega square plus 5 is equal to 5 upon minus 2.45 square plus 5, or x12 upon x11 is equal to R1 is equal to minus 5, where x12 denotes the mode shape of the second mass at the first natural frequency, and x11 denotes the mode shape of the first mass at the first natural frequency, and the ratio of these two mode shapes is equal to minus 5, where the minus sign indicates that these two modes or these two mode shapes are out of phase to each other and their ratio is equal to 5. Similarly, the second mode of vibration for the two masses is given by substituting the value of the second natural frequency, which is omega 2, is equal to 1.58 radian per second. In equation 3, we get 5x square is equal to minus 10 omega square plus 35 into x1, or x22 upon x21 is equal to R2 is equal to minus 10 omega square plus 35 upon 5, or x22 upon x21 is equal to R2 is equal to 2, where x22 is the mode shape of the second mass at the second natural frequency, and x21 is the mode shape of the first mass at the second natural frequency, and their ratio is equal to 2 with the positive sign, which means these two mode shapes are in phase with each other. So in this step, we find out the ratios of the mode shapes for the system at its two natural frequencies, but the values of the actual mode shapes are still need to be determined, and for this purpose we will calculate the response of the system, at the end of which the actual values of the mode shapes of the system will be yielded. Since we are provided with the general initial conditions for this system, therefore we are using the general solution for the general initial conditions, which are as follows. x1 of t is equal to x11 cos of omega 1t plus phi 1 plus x21 cos of omega 2t plus phi 2, and x2 of t is equal to r1 x11 cos of omega 1t plus phi 1 plus r2 x21 cos of omega 2t plus phi 2. So after taking the single derivative of the above equations of the general initial conditions and then substituting the initial conditions given in the question, which are x1 of 0 is equal to 1 and x2 of 0 is equal to 0, equations 5 and 6 are yielded. So from equation 6, the value of mode shape x11 is find out in terms of the mode shape x21 and phase angles phi 1 and phi 2, and then this value is substituted in the equation 5 such that we have x21 cos phi 2 is equal to 0.714, and it is called as equation 7. So after again substituting the equation 7 or value of x21 cos phi 2 in equation 5, we get x11 cos phi 1 is equal to 0.86, and it is called as equation 8. Now let's take the derivative of the initial conditions, which are x1 dot of 0 is equal to 0 and x2 dot of 0 is equal to 0, and substitute these initial conditions in the derivative of the general solution x1 dot of t and x2 dot of t. We will get equations 9 and 10, and from equation 10 we can find out the value of the mode shape x11 in terms of the mode shape x21 and phase angle phi1 and phi2, and this value of mode shape x11 is substituted in the equation 9 so that the equation 11 is yielded as follows: x21 sine phi2 is equal to 0. So after substituting this equation 11 in equation 9 again, we will get the equation 12, which is written as follows: x11 sine phi1 is equal to 0, and it is called as equation 12. Since from equations 7, 8, 11 and 12 it is evident that the mode shapes cannot be 0, therefore if we take the phase angles phi1 and phi2 equal to 0 in equations 7 and 8, then the actual values of mode shapes x11 and x21 will be yielded as follows: x11 is equal to 0.286 meters and x21 is equal to 0.714 meters. Finally, by substituting these mode shapes into the general solution of the harmonic equation, we get x1 of t is equal to 0.286 cos of 2.45t plus 0.714 cos of 1.58t, and x2 of t is equal to 1.43 cos of 2.45t plus 1.43 into cos of 1.58t. So with this lengthy problem comes to an end. Next we have another problem which states that an optical table with its contents weighing 147 newtons is to be protected against nearby vibrations by attaching a weight of 29.4 newtons with the table. The weight is attached using an elastic cable of stiffness 50 Newton per meter. The table is supported on 4 columns, each of stiffness 50 Newton per meter. Assuming vibrations take place in the vertical plane only, draw the 2 degree of freedom model of the given condition. Calculate the natural frequencies, the natural modes of vibration, and the response of the two masses if x1 of 0 is equal to 1 centimeter, x2 of 0 is equal to 0, x1 dot of 0 is equal to 0, and x2 dot of 0 is equal to 0. So this problem is related to the concept of mass damper. Therefore, it is very applied and has applications in real world scenarios. For example, in the start of this course, in the introductory lectures, I showed you guys the picture of a mass damper which is suspended from the ceiling of a building structure somewhere in Japan, and the purpose of this suspended mass is to control the vibrations of the building induced by the wind effects. So here we have an optical table which is supported on 4 elastic columns. Each has a stiffness equal to 50 Newton per meters. At the center of the table, a mass is suspended with elastic cable. The weight of the suspended mass and the contents of the table are given. So let's start the problem by first making the 2 degree of freedom vibration model as shown in figure. The model shows the stiffness element K equal to 200 Newton per meter, which indicates the 4 elastic columns on which the optical table is supported. The mass M1 denotes the mass of the optical table, which is attached to the stiffness element K. There is another mass M2 is attached with mass M1 through an elastic cable having stiffness is equal to 50 Newton per meter. So the formulation of equations of motion starts with the individual consideration of each mass one by one. So for mass m1, the free body diagram shows that the mass m1 is compressing the stiffness element k, and at the same time it is stretching the stiffness element Ka, which is in this case the elastic cable. Or in other words, the mass m1 is oscillating between the two nodes x1 and x2. Therefore, by applying the conditions of equilibrium on mass m1, we get summation Fy is equal to m1 x1 double dot. Here we are taking all the downward forces from top to bottom as positive forces. Hence, minus kx1 minus Ka into x1 minus x2 is equal to m1 x1 double dot, or after simplification the above equation becomes m1 x1 double dot plus k plus Ka into x1 minus Ka into x2 is equal to 0. We may call this equation as equation 1. Similarly, for mass m2, the same procedure is applied, and its FBD or free body diagram shows that the mass m2 is oscillating due to the stiffness of the elastic string and its own weight. So after applying the conditions of equilibrium on mass m2, we get summation Fy is equal to m2 x2 double dot and Ka into x1 minus x2 is equal to m2 x2 double dot, or m2 x2 double dot minus Ka x1 plus Ka x2 is equal to 0, and we may call this equation as equation 2. So equation 1 and equation 2 are the two equations of motion for this 2 degree of freedom system. Next, in order to find out the natural frequencies for this system, let's assume a harmonic solution for this system, or in other words, we can say that we are assuming the motion of the system as the harmonic excitation or harmonic motion. Since we know that for harmonic motion we have x1 is equal to capital X1 cos of omega t plus phi, and x2 is equal to capital X2 into cos of omega t plus phi, where x1 and x2 are the displacements of the two masses and capital X1 and capital X2 are the amplitude of the two masses. So by taking the double derivative of these highlighted equations and substituting the values of x1 double dot and x2 double dot in equations 1 and 2, equations 3 and 4 are yielded as highlighted. Also, equations 3 and 4 can be written in the matrix form as follows: matrix minus 15 omega square plus 250 minus 50 minus 50 minus 3 omega square plus 50 multiply by matrix x1 x2 is equal to 0. So the solution of equations 3 and 4 is only possible if the determinant of the coefficient matrix, which is highlighted in the red box, becomes 0. So after opening the determinant, we get an equation having 4 polynomial degrees as follows: omega 4 minus 33.33 omega square plus 222.22 is equal to 0. So for simplicity, we are assuming omega square is equal to z. Therefore, the above equation becomes z squared minus 33.33z plus 222.22 is equal to 0. Now this is a quadratic equation whose solution can be easily determined, and from the solution of this quadratic equation we have its two roots as follows: Z1 is equal to 24.1145 and Z2 is equal to 9.2155. So omega 1 is equal to under root Z1 is equal to 4.91 radian per second, while omega 2 is equal to under root Z2, which is equal to 3.04 radian per second. So in order to find out the natural modes of vibration, we may use the modified forms of equation 3 and 4, and by substituting the values of omega 1 and omega 2, the ratios of the natural modes of vibration can be obtained as follows. So from equation 3, we have x2 upon x1 is equal to minus 15 omega square plus 250 upon 50, and by substituting the value of omega 1 is equal to 4.91 radian per second in this equation, we get x12 upon x11 is equal to r1 is equal to 2.23, where x12 is the natural mode of vibration of second mass, which is the suspended mass at the first natural frequency, and x11 is the natural mode of vibration of the first mass, which is in this case the optical table at the first natural frequency. The minus sign indicates that these two natural modes of vibration are out of phase. So for the ratios of the second mode of vibration, the second natural frequency, that is omega 2, is equal to 3.04 radian per second, is substituted in the modified form of equation 3, that is equation 5, and we get x22 upon x21 is equal to r2 is equal to 2.23, where x2 is the natural mode of vibration of the second mass, which is the suspended mass at the second natural frequency, and x21 is the natural mode of vibration of the first mass, which is in this case the optical table at the second natural frequency, and the positive sign indicates that these two phases are in phase with each other. Next, we will find out the response of the system by using the general form of the harmonic motion for general conditions as follows. x1 of t is equal to x11 cos of omega 1 t plus phi 1 plus x21 cos of omega 2 t plus phi 2, and x2 of t is equal to r1 x11 cos of omega 1 t plus phi 1 plus r2 x21 cos of omega 2 t plus phi 2. So substituting the initial conditions, x1 of 0 is equal to 0.01 meter and x2 of 0 is equal to 0 as given in the question. The above responses are transformed in equations 6 and 7 respectively, and these equations are highlighted for your reference. And the simultaneous solution of these two equations, that is equations 6 and 7, yields the final form as follows. x21 cos phi 2 is equal to 0.005 and x11 cos phi 1 is equal to 0.005. Since these two equations indicate that the value of mode shapes cannot be equal to 0, therefore in order to find out the mode shapes, the value of the phase angles may be substituted as 0, such that at the phase angle 0, the trigonometric function cos will become 1. Therefore, we have x21 is equal to 0.005 and x11 is equal to 0.005 meters respectively. And after substituting these final values of the mode shapes, the general solution for the general conditions of this system becomes x1 of t is equal to 0.005 cos 4.91t plus 0.005 cos 3.04t, and x2 of t is equal to minus 0.011 cos 4.91t plus 0.011 cos 3.04t. So this general solution shows that at times the magnitude of x2 of t increases and greater than x1 of t, thus in turn suppresses the vibrations of the primary mass, which is in this case x1 of t. So with this result, this problem ends here. In the last, we have some more numerical calculations in order to prove that by attaching the secondary mass to a primary mass, the vibrations of the primary mass can be controlled. So let's consider the optical table as a single degree of freedom system, and we know that for a single degree of freedom system, the response of the system is given by x1 of t is equal to a cos omega n t, where omega n is the natural frequency, which is given by under root k upon m. Since k is the stiffness of the supporting columns and the table is supported on 4 columns, each having a stiffness of 50 Newton per meter, therefore k is equal to 200, and m is the mass of the table, which is in this case 14.96 or equal to 15 kilograms. So the natural frequency of the table or system is equal to 3.65 radian per second. Also, for a free undamped vibration system for a single degree of freedom system, the amplitude, that is A, is equal to under root x naught square plus x naught dot square upon omega naught square, where x naught is given in the equation as 1. Therefore, x1 of t is equal to x naught cos omega n t. So by finding out the actual response of the system, we just take any arbitrary value of time t. So let's take t is equal to 0.2 seconds, and the response of the single degree of freedom system, that is x1 of t, is equal to 7.45 millimeters. Now let's consider the system as a 2 degree of freedom system, and for that 2 degree of freedom system, we have already calculated its two responses, x1 of t and x2 of t respectively. Since we are interested here to find out the response or the vibration response of the primary mass, which is in this case the optical table, therefore we are considering the response x1 of t, and in this response we are taking the value of time as the same value which we were used in the above form for the single degree of freedom system, that is t is equal to 0.2 seconds. Therefore, the response of the mass m1 in a 2 degree of freedom system is equal to x1 of t is equal to 6.879 millimeter. By comparing these two results, that is the response of the system of a single degree of freedom and the response of the system for a 2 degree of freedom system for the same instant of time, that is 0.2 seconds, the displacement of the 2 degree of freedom system is less than that of a single degree of freedom system, which proves that by attaching an extra mass or a secondary mass to the primary mass actually reduces the vibrations of the primary mass. And with this numerical, the chapter ends here. If you like this video or have any suggestions regarding the improvement of the content quality, you may write me an email at sharos@cloud.neduet.edu.pk. Till then, stay productive and I will see you in the next lecture.